So in the last session, the theorem which we proved is this. The Galois group of the nth cyclotomic extension of Q or any field with characteristic 0 is isomorphic to the group of integers prime to and less than n with the multiplication modulo n. This is the theorem which we proved, and we have a very easy corollary. That is the Galois group of the pth cyclotomic extension of Q is cyclic and contains p minus 1 elements, where p is a prime number. This is a very quick corollary of this theorem. Here the number of integers prime to and less than n when n is a prime is n minus p minus 1, and that is what this one is, and it is a cyclic group because it is a prime number. So there is nothing to prove here, just a corollary, because sometimes you may have to use the corollary to solve problems. So let us do a couple of problems on this theorem on the Galois group of cyclotomic extensions. The first one we are going to try is show that the 20th or so that the group of or the Galois group of 20th cyclotomic extension of Q is isomorphic to Z2 cross C4. So the theorem says that, using the previous theorem, theorem the Galois group of, or you can say the Galois group, Galois group of 20th cyclotomic extension of Q is isomorphic to the group of integers that are prime to 20 and less than 20. That is 1, 3, 7, 9, 11, 13, and 17, 19. 1, 2, 3, 4, 5, 6, 7, 8. Yeah. So this is a group of 8 elements. Okay. So this let's say G is equal to this. So G is a group, actually an abelian group. An abelian group, okay, or you can say a finite abelian group of order 8. So that means G is finitely generated because it's already a finite group, so it definitely has to be finitely generated. Okay. So we are going to borrow a result from group theory, that is a fundamental theorem of finitely generated abelian groups. So the theorem says actually the finitely generated abelian group, any finitely generated abelian group is isomorphic to Z p to the power of r, Z p to the power of 1, P1 1, P1 r to the power of 1, P2 r square dash dash, P n rn dash Z cross let's say k times. This is the fundamental theorem of finitely generated abelian groups. So here we have a finitely generated abelian groups of 8. So G has to be isomorphic to either Z8 or Z2 cross Z4 or Z2 cross Z2 cross Z2. This is the only 3 ways that this could be isomorphic. But Z8 is cyclic. and G is not cyclic. G is not cyclic. Okay. And we have an element 3 in G that has an order 4, meaning 3 to the power of 4 is equal to 1 in here. 3 to the power of 4 is equal to 81 mod 20, and that is 1. So, but Z2, if you take this one, in every element is of order 2. If you take any element from here, the elements of Z2 are 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 0, 0, 1, 1, 1, 0, 1, 1, 1, 0, 1, 1, 1. If you take any element, its square is 2, or the order of any element is 2. But we have an element in here that has an order of 4. 3 square is not equal to 1. 3 square is 9. So that means G is isomorphic to Z2 cross Z4. And of course, if you take Z2 cross Z4, you'll find that there are elements that has got order 4. See, one of the elements of Z2 cross Z4 are 0, 1, 0, 0, 0, 1, 0, 2, 0, 3, 0, 4, sorry, 0, 4, not 0, 4, then 1, 0, 1, 1, 1, 2, 1, 3. These are the elements here. And if you take this element and this element and this element and this element, they are all order 4. So the order of this is 4. 0, 1 plus 0, 1 plus 0, 1 plus 0, 1 is equal to 0, 0. So that means we have elements in here that has got order 4. And we can find the same number of elements here whose order is 4. 3. Besides 3, there are another 3 more elements. I am not going to compute that, but there are. But this theorem says that this has to be isomorphic to one of these, and this is not isomorphic to here, and this is not isomorphic to this group. So it has to be isomorphic to this. And that's the. We'll do one more problem on this. Compute or the Euler's function of 8100, or we can say find the order of 8100th cyclotomic order of the Galois group of order of the Galois group. Galois group of 8100th cyclotomic extension of Q. So the idea is, actually this is not a problem in the cyclotomic extensions, because this is actually compute the numeric value of this, and we know that if n is equal to 2 to the power of v times p to the power of s1 times p to the power of p2 to the power of s2 times p t to the power of st, if n can be written like this, then the Euler function p of n is equal to 2 to the power of v minus 1 times p1 to the power of s1 minus 1 dash dash pt to the power of st minus 1 times p1 minus 1 plus p2 minus 1 dash dash pt minus 1. So this is actually a result from number theory. All we need to do is you factorize 8100 like this. So we need to find out the factorization of 8100. So 8100, if you 2, it's going to be 4, 5, 5, 0, right? 4, 0, 5, 0. Okay, I will write it like this. 8100 to 4050 2025 3 is 6 22 7 55 3 2 2 5 again 3 7 5 3 25 5 5. So this is actually 2 square times 3 to the power of 4 times 5 square. So phi of 8100 is equal to 2 to the power of 2 minus 1, that is 2, then 3 to the power of 3 cube times 5 times p1 is 3 minus 1 2 times 5 minus 1 4. So this is going to be 54 times 5 times 8, that is 54 times 40, and that is 21. So we'll do another problem. Let K be the splitting field of x to the power of 12 minus 1 in Q. Then find G of K over Q. Galois group of K over Q. And also show that sigma belongs to G of K over Q implies sigma square is equal to I, the identity element of this Galois group. Or you can say, show that the order of every element in G of K over Q is 2. So K is the splitting field of splitting field of x to the power of 12 minus 1 in Q implies K is the 12th cyclotomic extension of Q. So that implies G of the Galois group of K over Q is isomorphic to the group of integers less than 12 and prime to 12 under multiplication mod 12. So that is actually G of K is isomorphic to 1, 5, 7, 11. Yeah. Mod multiplication mod 12. So we found this group, so this part is done. Now we need to prove that an element from here in this group is of order 2. So you take any element from here and show that it's of order 2, then you are done. So 5 square is equal to 7 square is equal to 11 square is equal to 1. 25, this is actually mod 12. It's 25, so it's 1. 49 is 1. 121, it's 1. So that implies sigma belongs to G of K over Q implies sigma square is equal to I. So we'll do another problem. Find the third cyclotomic polynomial in Z3. So let us go through the definition of the cyclotomic polynomial. The definition goes like this: if alpha 1 dash alpha phi of n be the nth primitive root of unity in F, then the cyclotomic polynomial is defined as capital phi n of x equal to pi I is equal to 1 to phi of n. This phi of n is the number of integers less than n prime to n, x minus alpha I. So basically what we need to do is to find out the third primitive roots of unity in Z3. So we need to find out the third primitive roots of unity in Z3. And how many of them are there? There are two, because phi of 3 is equal to 2. The third root of unity in Z3 are the zeros of x cube minus 1. There are 3 zeros here, out of which 2 of them should be primitive roots, and that the only one remaining is the 1. So alpha not equal to 1, if alpha not equal to 1 is a third root of unity, then it is third primitive root of unity. And if alpha is a root of unity, then alpha is a, if alpha, and of course you can say, then alpha, that also implies alpha is a root of x cube minus 1. Then alpha square is the other 0 of x cube minus 1. So the primitive root, third primitive root of unity in Z3 are alpha and alpha square. So the cyclotomic extension phi 3 of x is equal to x minus alpha square. And that is again is going to be equal to x cube minus 1 by x minus 1. And if you divide this one, this is going to be x square plus x plus 1. So this is the cyclotomic, third cyclotomic polynomial in Z3. We'll do another problem. Find the number of elements of the splitting field of x to the power of 6 minus 1 in Z3 of x. What is the definition of splitting field of this? it is the smallest extension of Z3 that contains all the zeros of x to the power of 6 minus 1. So x to the power of 6 minus 1 actually can be written as x square minus 1 whole cube in Z3 of x. Because if you expand this one, x square minus 1 cube is equal to x to the power of 6 minus 3 times x square x to the power of 4 times 1 plus 3x square times 1 minus 1. And this is 0 because this is 3 here. So this is actually x to the power of minus 1. So this is actually equal to x minus 1 whole cube, x plus 1 whole cube. So the zeros of x to the power of 6 minus 1 are plus or minus 1. And both belongs to Z3. Because minus 1 is 2. So that implies Z3 is the splitting field of x to the power of 6 minus over Z3. So for the number of elements of the splitting field of x to the power of 6 minus 1 over Z3 is our next problem is find the 12th cyclotomic polynomial in Q of x. So the nth cyclotomic polynomial is defined like this, is phi n of x equal to pi of 1 to Euler function of n, that is the number of primitive or the number of integers less than n and prime to n, x minus alpha I, where alpha i's are the primitive nth root of unity. So before we do this, we established a general result. So the first claim is this: phi n of x equal to the product of all cyclotomic polynomials d of x, not I'm sorry, this is actually xn minus 1, where d divides n. What I mean by this one is, we'll take an example. X to the power of 8 minus 1 is actually equal to x to the power of 4 plus 1, x square plus 1, x plus 1 and x minus 1. So this actually is this is actually phi of 1. This is phi of 2. And this is phi of 4. And this is phi of 8. See, there is 8, 4, 2, 1. They are the divisors of 8. So the only divisors of 8s are these 4. That's what I meant here. So let alpha 1 dash dash alpha n be nth root of unity in Q. So this includes some primitive roots. So this implies that alpha 1 dash dash alpha n forms a cyclic group generated by any of the nth primitive roots. And for any alpha j, for any j, j 1 less than or equal to j less than or equal to n, alpha j generates a subgroup of, let us take this as G. And so for D divides n, meaning the n is a multiple of D, D divides n, alpha to the power of n by D will be the dth root of unity. Primitive dth root of unity. See, if alpha 1 dash dash alpha n are the roots of nth roots of unity, then this implies x to the power of n minus 1 is equal to x minus alpha 1 dash dash x minus alpha n. So, see if, for example, here, if you take d is equal to 2, n by d is equal to what? So this is actually, if you consider the roots, zeta be the primitive 8th root of unity, then square, cube, 4, 5, 6 and 7. These form a another one, 8. This is actually going to be 1. So this form a cyclic group. Okay. So these are the primitive roots. Okay. Now if you take d is equal to 2, n by d is equal to 4, that means you are taking this one. So this is actually what? This is actually our I, and this is our minus 1. This is our minus I. right? So n by d is equal to 4. That means set of 4 is second primitive root of unity. What is set of 4? It's -1. And -1 is definitely the second primitive root of unity. That's what I'm saying here. And if you take d is equal to 4, n by d is equal to 2, and that is I, so zeta square is fourth primitive root of unity. So if you take the collection of all such devices, so the collection of all, or I'll write the root of unity. So collection of all primitive roots of unity collection of all dth primitive roots of unity contains all nth root of unity. What I am trying to say here, if you take 2, 4, 1 and 8, those are the, if you take all, see 2 is, if d is equal to 2, then n by d is equal to 4, so this is one of them, and minus I is another one. So these two are when d is equal to 4, and this one and this one, this is actually equal to not this one. This one will be d is equal to 2. So that's what I'm saying. So if you collect all this stuff, you are going to get, when you take the all primitive dth roots where d divides n, you are going to run through all these zeros. Contain all the nth root, and that implies x square x to the power of n minus 1 is equal to pi of d divides n phi of d x. See, that is exactly what I am saying here. Okay. Now, using this result, let us compute the 12th cyclotomic polynomial. This happens when the characteristics of the field does not divide n. But here the characteristics of the base field is 0. So we are okay with that. Now, let us compute, let us find out what are the divisors of this. 12 has got, the divisors of 12 are 1, 2, 3, 4, 6 and 12. So, by this definition, x to the power of 12 minus 1 is equal to phi of 1 of x, phi of 2 of x, phi of 3 of x, phi of 4 of x, phi of 6 of x, and phi of 12 of x. So we need to find out what are things we can find from here. Let us take phi of x, phi 1 of x. This is actually x minus 1 because 1 is the first primitive unit of unity. Second one is going to be x plus 1 because minus 1 is the primitive second root of unity. Okay. Now let us take phi of 3. Phi of 3 is equal to x cube, to find out phi of 3, what we will do is use this rule. So what are the divisors of 3? 3 divisors of 1 and 3. So phi of x to the power of 3 minus 1 is equal to phi of 1 of x times phi 3 of x. Phi 3 of x. So that is equal to, this is x minus 1 phi 3 of x. So phi 3 of x is equal to x cube minus 1 by x minus 1, and that is x square plus x plus 1. We know that phi of 4 of x is equal to x square plus 1. Because the root of this is minus plus or minus I. And that is the lowest, 4 is the lowest degree, so that it will become 1. Now we need to find out phi of 6. So phi of 6, to find out phi of 6, we will use the result again. That is x to the power of 6 minus 1 is equal to phi 1 of x, phi 2 of x, phi 3 of x, phi 6 of x. And this is actually x minus 1, x plus 1. This is x square plus x plus 1. And this is phi of 6x. So phi 6 of x is equal to x to the power of 6 minus 1 by x minus 1, x plus 1, x square plus 1. And that is, if you compute, that will be x square minus x plus 1. Now, we need to compute phi 12 of x, and we have this one, all the 5 of them except the last one. So I'll take some space here. So x to the 12 minus 1 is equal to phi 1 of x times phi 2 of x times phi 3 of x times phi 4 of x times phi 6 of x times phi 12 of x. And this is x minus 1, x plus 1, x square minus plus x plus 1. This is x square plus 1, and this is x square minus x plus 1, and this is phi of 12x. So phi of 12x is equal to x to the power of 12 minus 1 divided by x minus 1, x plus 1, x square plus x plus 1, x square plus 1, x to the power of x square minus x plus 1. So this is of degree 12, 1, 2, 4, 6 and 8. So the result will be a polynomial of degree 4. I am not going to compute this one. This is an elementary polynomial division. The answer will be x to the power of 4 minus x square plus 1.